Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. Today, actually, it is my first video in this channel, and I wish that I make very nice, clear video. I have chosen a very common statistical topic, which is one-way ANOVA. It is very common in research. Researchers usually they hear ANOVA. Maybe chi-square, regression, all these are common. And I have chosen the one-way ANOVA because it is simple, simpler than maybe most of the other methods. Okay, so let's start. So this is our topic. This is one-way ANOVA. Okay, what is the one-way ANOVA? What does it talk about? One-way ANOVA is some statistical method or statistical technique. You may understand it as calculations, some mathematical, statistical calculations. And the aim of all these calculations is to prove or to make sure that there is a relationship between two variables, provided that one of the variable is categorical versus the other variable is continuous. Continuous means numerical. Categorical is any variable that cannot be valued. Let's say city, the city variable. If we say that this guy belongs to or lives in this city, let's say A, city A. This is categorical, very pure categorical. The other guy lives in city B, and another guy lives in city C. Okay, so this is categorical. Or if we say that this guy is male and this lady is female. Male and female, I mean the gender variable, which contains two values or two possibilities, male and female. Male and female are categories, so the gender variable is categorical. They are not values, okay? Continuous means anything like salary, weight, height. All these are continuous or numerical. They are values. Let's make this clear by imagining that we have a spreadsheet or some database of so many individuals. Let's say 200 individuals. 200 individuals. This is individual number 1, individual number 2, individual number 3, number 4, etc. And this is the city of each individual in this column, and this is the salary. Okay, so for example, individual number 1, he lives in city A and his salary is 2,000. Okay, individual number 2, let's say that he lives in city C and his salary is 900. This one, let's say again he's in C and his salary is 1,100. This one belongs or lives in city B, and let's say that his salary is 1,600, and etc. There are so many individuals in this database or the spreadsheet. Okay, let's now go a bit deeper into mathematics. Let's open another page. Okay, let's draw the XY axis. The x-axis is represented by city, and this one is salary. Okay. And here, city, we have city A, city B, and city C. And we want to make bars. A bar next to each city. So city A will make a bar that represents the average salary for this city. Let's say that it is 2,000. Let's say 2,000. This is the average salary for city A. How about city B? City B, let's say that the average is 1,500. And how about city C? City C, let's say that the average is 1,000. Okay, and here we have, let's say, the grand average. Let's say that the grand average is 1,600. The grand average is the average for the whole sample of individuals. For all the individuals that we have in the database, the 200, for example, 200 individuals, regardless of their cities. We don't split them by cities. We take the average for all the individuals, regardless of the city. We don't care about the city. Okay, let's say that it is 1,600. Okay. Now the whole picture that we created, the whole picture represents a model. Why do we call it a model? Because we simplified the whole problem or the whole data into some simple model in a simplified way. We considered that each city, the salary in each city is summarized by an average. And the average is nothing but the center of the values of the salaries. So each city, we simplified or summarized the salaries in each city by one single value. We made things more simple. That's why we call it a model. The whole picture that we have created is called a model. By simplifying the salaries in each city by one single value, which is the average. Okay. Now let's go more into details of participants, or sorry, the individuals. Let's say that there is an individual here in city B. There's an individual here with a salary of 2,000. Of course, we have an individual here, and we have an individual here, and maybe some individual in this position. So many individuals, but the center point is this average. 1,500, this is the average. So, if we are blind, blindly took this individual, and we don't know his salary, what would we expect? If we just took him blindly, we don't know his salary. We will expect that his salary is this one. According to our model, we will expect it to be 1,500. Okay, this is our expectation. And this is the actual. 2,000 is the actual, and this is our expectation. So here comes the term error. Here comes the term error. So let's write it here, error. We have made an error, and the error is the difference between 2,000 and 1,500. What is the error? It is 500. It is the distance between this and this. Okay, between 2,000 and 1,500. This is the error. Okay, now another term that we should talk about is this one. The difference between this model value and the grand average. So we said that blindly we think that we expect, if we are blind, we expect that anyone like this guy with the 2,000 salary, if we took him blindly, we will expect that this is his salary, 1,500. How much this value is far from the grand average? The grand average is the stupid average. Is very stupid average. Why it is a stupid average or naive? In statistics, they call it naive. It is naive average. Why? Because it doesn't care about cities. It doesn't consider any other variable in the calculation. It simply calculates the average for the whole sample without any try to be somewhat intelligent. So it is a stupid average. And of course, we want our model average, this average for the city, for all the cities, we want it to be away from this stupid average. So we wish that this one is away from this stupid average. We wish that this value is far away from this stupid average because it is stupid. So and of course we want to be away from anything stupid. Okay. So how far we are? So for this individual, we said that the error is 500, and we expect for him, if we don't know his salary, we will expect 1,500. And how far it is from this stupid average? The expectation, it is minus 100, because we subtract the grand average from this one, the 1,500. It will be, let's call it M. This difference we will call it M, which stands for model. It is minus 100. Okay. Like that, we will do the same thing, the same calculation of differences for all the individuals from all cities, from all cities, for all the 200 individuals in the sample. We will calculate same things here. We'll do the same. Okay. And we have a problem, because the values here that we calculate for all the individuals, they are a mix between negative and positive values. And because of that, they would cancel each other. the positive and negative values, they'll cancel each other and we'll get 0. If we sum them up, we'll get 0. So we will square all the values. We will square them to get rid of the negative values. So after that, we may safely we may sum them up safely. We will get a sum here. We get the sum to summarize all of these values. To summarize them, we sum. We add them up. We add them up and get a summation. Okay? And this happens after we square the values. We square them and then sum all the values up. Okay? And we will call this sum, see this sum, the first sum, we will call it by common sense, it is sum of squared errors. Sum of squared errors. Okay, and we will call this sum, the second sum, we will call it sum of squared model. Sum of squared model, okay. Sum of squared model, okay. And of course, we want the sum of squared error to be small because it represents the errors in our calculations. Because it represents the errors, we want it to be small. We wish it is small, okay? And we wish that this one is large. Because it represents or it means how far we are from the stupid or naive average, the grand average. And the more we are far from it, and which means that we are far from stupidness, from being stupid. So we want this to be large and we want this to be small. Okay, let's create another page. Okay. Okay, we have sum of square errors. Let's say it is maybe, let's say 20,000. Let's just an example. And sum of squared model, let's say that it is 1,000. Okay. And here we know that this value, this big value, it is the sum for so many individuals, 200 individuals. It is the sum of values for so many individuals, 200. So why don't we summarize it and make it simpler by averaging it, getting the average of this sum? So by common sense, most of the people will think that we will divide it by 200 because we have 200 individuals. Especially the non-statisticians, they'll think that we will divide by 200, which is a common sense. But we subtract 1. We subtract 1 from this 200. Okay, so you'll get 20,000 by 199. Why did we subtract the 1 from the number of individuals? This is not our topic now. This is related to some theoretical issue in statistics called degrees of freedom. So we'll not talk about it, but we'll subtract 1 from this 200, okay? And we'll get what? I think we will get something like 100 approximately. And here we divide by 3 minus 1. 3, 3 because we have 3 cities, 3 cities, and 1 because we have one grand average, one grand average. Okay, one grand average we have. So 3 minus 1. Again, why did we cancel the 200? We cancelled it and we relied on this 3 minus 1. Why? This is not our topic. It has some statistical justification and related to degrees of freedom. And this is not our topic. We can talk about it sometime later. But just know that it is 3 minus 1 and it replaced the 200. It replaces the 200. We just 3 minus 1. So this will, after averaging, this will not be any more sum. We will not call this sum because the first letter stands for sum. It will be mean, which means the average. Mean. So it will be mean squared error and mean squared model. So we'll have mean squared error, which is 100, and mean squared model, which is will be 500. Okay, again, we want this average, this one, we want it to be large, and this is because this one represents the errors. Okay, the errors in our problem, we want it to be small, and we want this to be large. Okay. Okay, to make a judgment, we make a ratio. We'll call this ratio F, or F ratio, or F. Okay, ratio by dividing the 500 over the 100. And of course, we want the numerator, just as we said, we want the numerator to be large and the denominator, we want it to be small. So we want the whole result, which is 5, the whole result, we want it to be large because it is the division of the 500 over the 100. We want it to be large because large means that the numerator is large. Being large, the result, if it is large, this means that the numerator is large. And this is what we want. So now let's judge. Is this 5 big? Is it big? Actually, we can't decide. You can't say that it is big or small. It is very subjective to talk about this thing. It is subjective. We can't decide. Okay, let's make another page, a new page. Okay. So we can't decide. We have an F ratio of 5. Is it large? We can't decide. The solution for this is to convert this to p-value. Conversion is pure statistics. It is related to the F distribution. This is not our topic now. But let's now just simplify the thing. P-value ranges between 0 and 1. It is a standard value. That's why it is easy to evaluate than evaluating just 5. This one is very standard. It is standard and easily evaluated. After the conversion, let's say that the conversion resulted in a p-value of this one. This is the p-value. P-value, it is 0.044. We want this p-value to be small. We want it to be very small, close to 0. Let's say that we want it to be less than 0.05. This is our criterion for being small. We call it level of significance. It is the criterion for being a small p-value. Let's say that it is our criterion or level of significance is 0.05. Okay, so this one of course is smaller than 0.05, so this value is very small. P-value is very small. I'm sorry. Okay, if it is smaller than 0.05, what do we conclude? We conclude that cities are significantly different in salaries. Okay, or in other words, we may say it in this way: the variable city is significantly related or associated to salary, the salary variable. Okay, if this value is large, if the p-value is larger than 0.05, we cannot prove this. We fail to prove that cities are significantly different in salaries. And we fail to prove that city is significantly related to salary. We fail to prove this. We can't prove this. Okay? Okay, we reached the end of this topic, and I said that it is my first video on this channel. I wish that it was easily presented to you and things were clear. We meet you in the next video, inshallah. Goodbye.